Next up, we have Kelley Rivoire, who is the head of data at Stripe. So she will be talking about utilizing AI products with machine learning infrastructure. So join me in welcoming Kelley to the stage.
All right, thanks, Daniel, for the introduction. I work on data and machine learning infrastructure at Stripe. And I'll tell you about some of the challenges that we faced at a platform level in building production ML-based applications. I'll tell you a little bit about our specific solutions, but mostly I actually just want to talk about a couple of the problems. I think there are problems that are actually pretty common, but that are pretty subtle, and just kind of like understanding and learning more about how to think about them is pretty valuable in itself. Let's see. So I think it's useful when talking about platform level problems to start by looking at them through the lens of a particular example. So I'll kind of tell you a little bit about one of Stripe's products, Stripe Radar. Stripe overall aims to provide tools for starting and running internet businesses, and a big piece of that is payments. And then one of the kind of things that's true about payments is that you want to make sure that the payments you're accepting are legitimate payments and not fraud. And so Radar is our fraud product. So basically, if you're a business who accepts payments through Stripe, every time you send us the information for a transaction, we don't just check with the credit card networks or whatever the appropriate bank is that they're going to approve the transaction. We also evaluate in real time in that cycle, like, do we think the transaction is a good, legitimate transaction? And if we don't, we can maybe block it for you or send it for you to review in a queue. And ultimately, we produce a risk score, which is like the probability that this charge is fraudulent. And we do this pretty quickly. It says less than half a second, but it's probably more like 100 milliseconds or so in most cases. And this is based on a lot of different types of data. Some things are pretty obvious, like what is the amount of the transaction? Some things are less obvious, maybe behavioral data, like if you type in a weird way, maybe it's more likely that you're a bot. And then some of the unique value we can provide is by having this historical data, like not just for your business, but for all businesses that use Stripe. So for example, if the credit card that was used in the transaction has been used in the past hour from IPs in 5 different countries across a bunch of different businesses, like that's probably not a good sign. And so definitely we do a lot of work toward training models, evaluating models, optimizing models, and deploying them. And I think the kind of external ecosystem has evolved really quickly in that area. So there are a lot of good libraries and tools that you can use. So I'm actually not going to talk about that, even though that's pretty interesting itself. I'm going to talk a little bit more about a couple of problems we faced, like a little bit outside the black box, kind of at the interfaces, in kind of having good inputs and knowing how to understand the outputs. So the first problem that we spent a lot of time thinking about is how do you even get that input to your model? And this will be particularly relevant to applications that are a little bit like fraud, where you have some kind of sequence of events that you're going to use to form your training data or to evaluate. That's true for other applications, like if you're trying to predict click rates or make recommendations. It's less true if you're trying to do image or speech recognition. So when a lot of people think about ML, this is kind of what they think about. Let's say you took Andrew Ng's Coursera class. You're kind of given this matrix that has a bunch of different rows with observations. And then there are different values for features, and then there's a label, good or bad. And there's just this really nice matrix that represents ground truth about reality. And then your job, if you're developing the model, is to fit the n-1 columns to the nth column with the label, and to do it in a way that gives you a model that will generalize to other inputs. And that might be something really simple, like a decision tree on the right. It might be something really complicated or fancy, like maybe some recurrent neural network or something. It doesn't really matter. But a lot of times people think this is always the hardest part, but actually sometimes this is the simplest part. And the hard part is sort of how do you get the data that you produce that matrix from? Because often what you have is more like this giant pile of serialized data that you have to kind of do a lot of work to turn into a sane matrix that you can train from or score from. And there's a lot of reasons why this is hard in the real world that are pretty interesting. One is, you might have some of your data in different databases. Maybe you actually kind of like mutate those records and they change over time. Maybe you have some data in logs or event streams. I see some nods. And then there's this question of like, how do you pull all that together? There's a second kind of class of problems that basically kind of acknowledge the difference between like when you score and when you train. You want to make sure when you're training that you're looking at data that represents the state of the world at the time the prediction would have been made, not the state at any time since, which is actually harder than you'd think. I'll talk a little bit more about that. And then a lot of times, like because training, you're kind of trying to process all of this data with high throughput. And in inference, sometimes what you care about is really quick individual predictions. People often use pretty different systems for training and scoring. So you might have different data in some cases between the two. You might have different code. They might be written in different languages. And all of these things can kind of make the prediction of what you actually evaluate in your real application worse than what you expected in sometimes pretty surprising ways. One of the particularly pernicious problems is this problem when you kind of are pulling data from the future unknowingly into the past. A simple example from the fraud case is kind of shown here. So let's say I'm like a machine learning engineer and I have a great idea for a new feature for my fraud model where I think it might be really predictive if we look at the fraud rate associated with a given customer's email for that business. And so like the sequence of events that I might be looking at is that maybe somebody, Kelley at Stripe.com, made a couple of purchases on a couple of different businesses using a stolen credit card. Eventually, the owner of that credit card realized and disputed the charges. And now I have this great idea that I have this feature based on fraud rates, and I calculate the fraud rates, and oh, look, like Kelley at Stripe.com, that's like a 100% fraud rate. So like that's going to be a really predictive feature. But the problem is that I didn't know that at the time the charges were made. Actually, the fraud rate at that time was 0. But it's really easy to kind of make different types of mistakes like that sort of leak this data through and that make your model worse and worse in unexpected ways. And so the way that we've kind of chosen to think about this at Stripe is to kind of constrain like a little bit of a closed world system where we have an API for writing features that really only has like 2 core types in it, features and events. Events are data that's associated with a particular point in time. So that's kind of like the vertical lines here. And feature is basically like a fact about a subject that can be evaluated at any point in time. So as an example, like maybe my subject is the business, and I have like a key of that, and then I might have values where I track what is the sum dollar amount of the transactions for that business, and like maybe the number of transactions, and then later I could transform that to get the average transaction value for that business. And then basically kind of all I do is like in this API, I can kind of make different transformations between features and events. And because the event is timestamped and it's a read-only timestamp, like kind of all I can do, I can sort of limit it so that I'm only ever using events like up to the time that I'm interested in evaluating. And so I can't kind of by construction make this mistake where I'm like taking something from the future into the past. So basically, then the training data becomes like features attached to events. On an event, we can look up the feature value, and then basically that's kind of how we do everything. One of the important things here is that this requires all of our inputs to be evented data, something that's logged, it's mutable, it doesn't change, it has a timestamp. And then just to tell you a little bit more about what we actually do, basically we use this API based on features and events for defining the business logic of a feature. And then we kind of make an abstract syntax tree out of that and basically like compile it to run on different backends. And this also kind of helps us solve the problem of different business code running in training and in real time for scoring, because that business code is kind of only written once. And then we can also do pretty extensive checks to make sure that our compilers to different backends like produce the same results. This is actually what we use for Radar. We use it to produce pretty big kind of graphs, feature graphs of features and events. And with our push-based real-time backend, we can update these pretty complex features graphs like fairly quickly with a P99 of probably less than 100 milliseconds, updating 100 keys. So the second problem I want to talk to you about is more like at the output side, whereas the first one was kind of like, how do you get this data to even put into your model to begin with? The second is like, okay, let's say you evaluated this transaction and the risk score is like 98. Now what? And like, what if you think that's wrong? What do you do with that? And you might ask kind of like, why do you even care about that? Like, if the model is good enough overall, why does it matter why a decision was made? Like, isn't that what machine learning is for? And that's kind of partly true, but partly not true. Like, one thing that is really predictive of being able to make your models better is that you can iterate faster and debug them. And if you think a decision is wrong, but you kind of don't know what went into it and can't investigate it, then it's kind of hard to know, like, did you have a bad input? Did you have a time traveling feature problem, for example? Is there some bug in the model? Is there some other problem? The other reason you might care is that a lot of times you're not just like acting on a model in an automated way. Like, a human may be in the loop and they may be kind of using the output of that model to then do something else. Like, for example, we heard earlier, maybe a radiologist is going to take a look at a prediction of what modality they might want to use to image. And if they don't understand or they're suspicious of what led to the score, they just might not trust it, or they might make a worse decision than they would if they had some additional information about why. So understanding models and what the output is can help us iterate faster and ultimately kind of improve the performance of the system that we care about. One solution to this that can actually be pretty effective is just like, don't use complicated black box models, like only use simple models that you can really understand everything that's going on. So that could be a decision tree like what's shown here. It could be something like a logistic or linear regression. There are some pros of doing this, but also some limitations. If you're thinking about decision trees, shallow trees are sometimes not very accurate. If you have really deep trees, it's actually not that interpretable. It's easy to overfit to a training set. And then in some cases, you want to be really transparent about your model, but in other cases, you don't necessarily just want to give all the details to someone. For example, in the case of radar for fraud, we don't want a fraudster to be able to reverse engineer everything in our model, and therefore suddenly all the bad transactions get through. So we want to kind of provide enough detail to a business that they know what to do with it, but not so much that somebody can just totally reverse engineer everything we're doing. So one of the things we found is helpful is actually really simple. If you have a set of features that you do feel good about sharing, that's actually pretty valuable just to get some insight and to kind of help people understand and build trust and debug. So these are a couple of screenshots from the radar product in the Stripe dashboard, where on the left, there's kind of a nice display of information about the behavioral side, like what was the user agent, where is the UK user located relative to maybe where the business is, how many pages did they view or how long did it take them to check out. And on the right, there's a little bit more of the transaction-based view, which is actually pretty useful in this case. So you're kind of interested in the transaction at the top, but there's a bunch of related transactions we'll show. And this pretty quickly gets you to the insight that the same IP address made a whole bunch of different transactions with very slightly different email addresses, which is it kind of gives you something concrete to investigate. And it might be that the user is bad, or in some cases, maybe your integration is bad. Maybe you're accidentally sending the same email for every charge, which might lead to results that block charges that were actually fine. So this is actually really simple, but pretty useful. Another thing we try to do is just to give people some kind of reason, even if it's not a complete reason, for why a charge might have been blocked. So this is, again, a screenshot from our radar product for a charge that has risk evaluation highest. And the explanation is that the email address has been linked with an unusually large number of declined payments across the Stripe network in the preceding week. So it's very clear what that means. It's very clear how you might investigate it or what you might do with it or how you might think about it. And there are a lot of different ways that you can generate these types of explanations. We've tried some things in the past, just dropping out features and seeing how much the score changes, but that was kind of hard to evaluate in real time scalably. Or there are methods like Lime, where you kind of linearize the decision boundary, and then you kind of see what you could change to flip across the boundary, and then that's your explanation. What we found is useful for us is to do what's called kind of Posthoc explanations, where we train a simpler model based on the results of the more complex model. In this case, the simpler model is a decision tree. And the way you can think about this is that if you kind of trace through a decision tree, there are a bunch of different paths that lead to a leaf. And those are composed of a set of predicates, where the predicate is kind of like the true or false statement at each node. And then basically like kind of each of those possible paths is like a possible explanation. This means you actually have like potentially a large number of explanations if you have a decision tree that is wide or deep. So what we do is we kind of use an iterative process to limit that down a little bit and ultimately define a set of explanations that have like high recall over the entire data set and that individually have high precision. And then this kind of simpler model or explanation is something that we can easily evaluate in real time along with the more complex model, and that we can then use to show the reason in the dashboard. This is sort of interesting though, because it's like a reason. It gives you some insight about, maybe why was the charge blocked, but it's not totally the answer, right? Because like the reason the charge scored 99 and was blocked is because that's what the model evaluated it to be. So the model is like the real reason, but then the model isn't very interpretable. So this is what one of my colleagues likes to call like just so stories, where you can kind of like tell yourself that this is like why it was blocked, but it's like not totally true. So then you're kind of stuck with the question of like, does this matter? Is that okay? Is that not okay? And I think that depends a lot on the particular application. Like one question you can ask yourself is like, are you getting the information you need or that the consumer of the model needs to be able to use it, to iterate, to learn, solve these problems? You can also ask yourself, like, what's the impact of there being a wrong decision and not understanding it? So we heard a lot about medical use cases. That might be a case where you want a simpler, more interpretable model rather than a more complex one, because it's really important to get every decision right if it's life or death. Similarly, models today are used for predicting criminal recidivism. So if you're trying to decide like whether someone should get parole or stay in jail, it turns out that when people use complex models, sometimes there's a mistake and somebody stays in jail and doesn't get parole because there was a data entry error, which is pretty bad. So in that case, you might also want to kind of go with a more interpretable model. If you're doing something for us where it's like when something goes wrong, a charge gets blocked, that's not as bad. And so the trade-offs are a little bit different. And it's also kind of not fixed. Like sometimes you can sort of change that trade-off, where maybe when you block something and you're wrong, there's like a really easy appeals process, and that kind of like lowers the cost associated with a bad decision. So I think it's important to think about like both kind of what are your options or constraints for how you would explain something, or like do you need to do it quickly? But then also you can kind of think about the cost of a wrong decision to understand like whether you want a more complex model or whether you want something that is going to be more interpretable, even if maybe overall it's slightly less accurate. Okay, so stepping back, I think kind of the takeaways that I've had from learning about kind of these two types of problems, as well as other problems at the platform layer across all ML applications, is that like I think a lot of progress has been made on training, evaluating, optimizing, scoring models, and over a wide range of types, and making that like easier, faster, less expensive. But actually, when you're trying to productionize some critical ML application, there are a lot of other challenges. And like usually those challenges are kind of outside the black box model and sort of at the inputs and outputs, where you might want to spend some time thinking about what's going into your model. Is it repeatable? How do you know you're not making mistakes? What's in the output? How do you understand what's going on? And if that's going right, and then what's the feedback loop across all of that? Not just across training your model, but across kind of like the full system end to end of the application that you care about. So I'll stop there. I guess we have a minute or so. So if anyone has a quick question, I can try and answer that.
Do you have any thoughts on how these points pertain to unsupervised machine learning models as opposed to supervised that you're training explicitly?
Yeah, so the question is kind of about supervised versus unsupervised machine learning models. For us, typically, we're trying to predict, is this fraudulent or not? So there sort of is naturally a label associated with that, but that doesn't necessarily mean that, you have kind of like humans sitting there labeling, or that you don't use unsupervised learning as well. And I think you can kind of combine those things nicely, where like sometimes you can do things like train an embedding in an unsupervised way and then use that as an input to the supervised model, which is something that we've been exploring a lot more lately. And in that case, you will still have some of the challenges, like gathering your input data and using it in a sane way may still kind of be a problem in that case as well as in the supervised case. Yeah. Okay. All right, thank you.